Okay. I don't know. Okay, so anyway, is that any different than it was just a moment ago?
I think so. It's only in the green lines.
Okay, perfect. All right. Anyway, so good morning, calc friends. Spencer was the only one who was brave enough to be in here and dedicated enough, and unlike the rest of you slackers, he's here and you are all not.
It's lonely.
And he is lonely, although I'm here though too. So I'm moving this paper down here. All right, so what we're going to do today is not what I had planned to do today, but that's all right. We'll just make it up. It'll be fine-ish. We're going to do the area between two curves today, and we're going to do volumes of revolution. So, area between curves and volumes of revolution. So if this lesson here isn't quite getting it for you, then there's plenty of videos on YouTube to take care of that. Areas between curves and volumes of revolution. And we'll be doing the disk method today, and I hope the washer method if we are fortunate. Okay, so when we're finding the area between two curves, and I'm going to draw some generic curve here, f of x, and we have a curve g of x, which I'll just do that, just something a little different. And I want to find this area right in here between A and B. All I have to do is find the area under F and minus or subtract the area under G, which is down here, which I'm going to shade in red. That's all down here. And so once I find the area under F and I find the area under G, I subtract and I have the area between them. So we know from our integrals already that the area under F is the integral of f of x dx, and the area under G is integral of g of x dx. So if we want to find the area between them, don't ask me why I didn't capitalize that, I have no idea. Area between is the integral of f of x minus the integral of g of x. Or more simply, just subtract the two in the integral. And that's it. Nothing new. We already know how to integrate, and we already know how to subtract, so that's all we have to do. Find the area of the top, subtract the area of the bottom, and that's what's left in between them. So let's just do a couple of examples. Oh, and one other thing we're going to do. Area between curves and, oh, we already did average value. Okay, that's fine. We're good. Okay, so page 1, done. Let's do some examples. So let's find the area between f of x equals x squared plus 4 and g of x equals x on 1 to 3. So I'm going to draw a diagram for this. Don't need to, because we have the formula, but I'm just going to draw a diagram so we can see what's going on. So we all know what x squared plus 4 looks like. And we're going to square 3, 9, so we've got to go up to 13. So I'll just count by 2's here. 2, 4, 6, 8, 10, 12, 14 with 13 in the middle. So 2, 4, 6, 8, 10. And we got 1, 2, 3. Only going up to 3. So I'll draw f of x equals x squared plus 4 in blue. So that's going to have us here with the y-intercept of 4, and 3 will get us to 13. And we know it's quadratic, so it's curvy. So there is the beginning of our x squared plus 4 curve. I actually didn't have to go to 0. I should have started at 1, but I didn't. And then we have g of x, which I'll make in red. Oh, so I need to show the area of this. So underneath here, from 1 to 3. So we're just having the area right in here. So there's the blue area for f of x. Then I'll go red for g of x. So g of x is going to be y equals x. So that's going to be 1, 1, 2, 2, 3, 3, and so on. So we have actually 0, 0, which I don't need, 2, 2. Now the distances between points here are a little different on the x-axis and the y-axis. So we'll just have to make do. And we have 3, 3, which is right about here. And 1, 1, which is right about there. So this is all I need, just a little bit of a segment. So the area under there is, under where, is from 1 to 3 right there. So the area that we're interested in is right there, in between. So we have the total area under the blue, subtract away the area under the red, leaves us with the area between, which is what we're interested in. So, just using the formula, area equals the integral of f minus g. We'll just set up our stuff here. So we get x squared plus 4 minus x. So here's f of x, here's g of x, and we're going to integrate them from 1 to 3. So we just go ahead and integrate, and we get x cubed over 3 plus 4x minus x squared over 2, evaluate from 1 to 3. So we plug in 3, and we get 27 over 3, which is 9, plus 4 times 3, which is 12, minus 9 halves, minus, now plug in 1, 1/3, plus 4, minus 1/2. And just grinding out the work here, we got 21 minus 4.5 is 16.5. And here we need 6s, so we have 2/6 plus 24/6 minus 3/6, which makes 26 minus 3 is 23 over 6. So 16.5 minus 23 over 6. So, oh, that's not right. Oh, no, I'm good. Okay. So 23/6 is really 3 5/6. So 16 3/6 minus 5 5/6, making everyone into sixths. So we drop this down, 15. Not 13, 9/6 is going to be 4/6, so it's 10 2/3. Obviously I did some quick fraction stuff there, but I think hopefully we're all able to follow that, and hopefully I did it correctly. So the area of our shaded region right in between those two curves is 10 2/3 units. Just simple, straightforward, integrate the subtraction of the two functions, plug in the numbers, all done. Very simple stuff. So that's a pretty simple example. And a more complicated example comes in when we're not given the limits of integration and we have to actually figure those out. So an example of when we'd have to figure those out is when So I'm going to write up here, I'm going to title this diagram here, example of when you need to find limits of integration. So we'll have two curves here, one that goes like this, one that goes like this, and you'll need to find for yourself what that x value is and what that y value is. That's easy enough if we have f of x on the top and g of x on the bottom. In order to find those two, all we need to do is set f of x equal to g of x. And we'll be able to find our x's, and that'll be our limits of integration. And then we carry on just like we did just a moment ago. So let's actually do a problem like that. And I'm going to take it right out of Larson's calculus book right here. So we have f of x equals 2 minus x squared, and we have g of x equals x. And so again, right out of Larson's book here, I'm just stealing his diagram. And we'll graph the parabola 2 minus x squared. So that means our y-intercept is 2. And we graph something like this. And y equals x, of course, is 1, 1, 2, 2, negative 1, and so on. So what we need to do is find these points of intersection. And with any luck, they'll be nice numbers to work with. And from my graph, it looks like maybe they're 1, 1, and negative 2, negative 2. And as I'm looking at Larson's diagram, and the work up here, it looks like we're correct. But we need to make sure that we are actually correct. So we'll set them equal to each other. So we set 2 minus x squared equal to x, and figure out when they are going to be equal. So I'm going to add the x squared over here and subtract the 2 and rearrange the terms. So x squared plus x minus 2 equals 0. Factor, and we get x plus 2 and x minus 1, negative 2, positive 1. And so our limits of integration are, as we suspected, negative 2 and 1, because that's where f of x is equal to g of x. F of x is here, g of x is there, we set them equal and solved, and we have negative 2 and 1. So now we just go back to the formula that we used in the previous example and just grind through the work. So the area is equal to the integral from negative 2 to positive 1 of f of x, which is 2 minus x squared, minus g of x, which is just x. And we'll crank through that on the next page. So integral here, negative 2 to 1, I'm just copying again just so I don't get lost. 2 minus x squared minus x dx. As you can see, I do have all the notes if you need them. Oh, that's up too high. So we just go ahead and integrate. And I know that Spencer is way ahead of me already. Actually, he's not. He's just doodling over there because he's just waiting for me.
I just skipped the steps. I mean, I redid that, which I was supposed
Oh, you already integrated this?
No.
Oh, all right.
I just already.
Okay, go ahead. So, so he's going to integrate, and so am I. So we got 2x minus x cubed over 3 minus x squared over 2 from negative 2 to 1. So we'll plug in 1 first, and we get 2 minus 1/3 minus 1/2 minus, plugging in negative 2 next, negative 4 plus 8 over 3 minus 4 over 2, or 2. So 2 minus 1/3 is going to be 1 2/3 minus a half. So we got 1, I'm just doing some work up here. 1 2/3 minus 1/2. So 2/3 minus a half, we need some sixths here. So we got 4/6, 3/6, 1/6. So we got 1 1/6. So 2 minus a third is 1 2/3, minus a half is 1 1/6. Minus -4 combined with -2 is -6. Plus 8/3, so that's plus 2 2/3. So we got 1 1/6 minus, so -6 plus 2 2/3, so subtract, we got 3 1/3, so that's -3 1/3. So that's 2/6, so I can work with sixths here. So subtracting a negative is like adding a positive. So we have 4 3/6, or 4 1/2, which is the correct answer. So, and just going back to the diagram, so that's the area right in between these two curves right here. And that's what we just found. We just found that area. So, any questions so far? Anyone? Anyone? Spencer? Manette? Okay, great.
She'd probably ask something stupid.
Yeah, no, she wouldn't. Manette did a great job yesterday in reviewing calculus at PT while we were working together at PT. It was awesome. Okay, so let's do a trig problem.
Sarah's favorite.
Because we can. So here is another one right out of the book here. We are bounded by the region shown. Find the area of the, okay. Sine and cosine curves intersect infinitely many times. Bounded by the regions. Find the area of one of these regions. Okay. All right. So here's the example then. Find the area between sine x and cosine x. Between sine x and cosine x on the interval, on the, first interval that they intersect. That's a little confusing wording. I'm sure I could have worded it better. So a little diagram might be helpful here, as always. And I know Manette had a great time yesterday trying to visualize these diagrams. So here's our sine curve. I feel like Bob Ross. Happy little sine curve. Over here anyway, with a smile. And then we have the cosine curve. So there we are, doing our cosine curve. And so the region, the first region at which they intersect, goes from this point to this point, and we're finding this region right in here. We'll find the area of that region. So, there are two things going on here that we need to be aware of. The first is, we need to figure out what these points of intersection are. It's not going to be pi over 6. And we need to figure out what this point of intersection is right here. We'll get those in just a minute. And the other thing we need to recognize is, and sometimes it's obvious and sometimes it's not, but from this diagram it's pretty obvious, and I think the diagrams are really helpful here. When we are using our formula, the integral of f of x minus g of x, it's important to know which function is above the other one, and when, because sometimes they switch. One of the functions is above the other for one part of the region, and then it's below in the other part of the region. So it's important to know which one is above and which one's below. So in this case, we can see that the sine curve is really above the cosine curve for this entire region right here. So it's going to be important for us to set up the integral that way. So it's going to be sine of x minus cosine of x, because the sine of x is above cosine of x on this entire interval. So the question is, where do they meet? And hopefully we remember, and we should, that the sine of 45 degrees is root 2 over 2, and the cosine of 45 degrees is root 2 over 2, so it's really 45 degrees that we're talking about here, or pi over 4. So pi over 4 radians for there. And we also have pi over 4 radians, or 45 degrees, in, here's quadrant 1, here's quadrant 2, and here's quadrant 3. So we're in quadrant 3, so we got a 45 degree angle in quadrant 3, which is 225, or 5 pi over 4. So 5 pi over 4 is the other place that we got, 5 pi over 4. So again, remembering that we just convert, so we have 225 degrees, and we just put pi next to and 180 underneath, and we should get, oh, hold on, I'm on drugs. So 225 over 180 equals radians over pi. There we go, that's better. Yeah, 225 pi over 180. Oh, 5 pi over 4. Good, I was right. I was right the first time. Yeah. So put pi next to and 180 under, and that's how we convert degrees to radians. So 5 pi over 4. So we're going to go from the lower, which is pi over 4, to the upper, 5 pi over 4. So we'll copy this on the next page. And we get area equals the integral from pi over 4 to 5 pi over 4 of sine x minus cosine x dx. And so we go ahead and integrate. And so the integral of sine is negative cosine. And the integral of cosine is sine. And we're doing this from pi over 4 to 5 pi over 4. So putting in 5 pi over 4, aka 225 degrees. So the cosine of 225 is negative root 2 over 2. But this is already negative, so it's going to be positive root 2 over 2. And then we have, putting in pi over 4, so the cosine of pi over 4 is root 2 over 2, but it's negative, so this is negative root 2 over 2. So I put in 5 pi over 4 right here. So putting in cosine of 5 pi over 4 gets us same as cosine of 225, which is negative root 2 over 2, because we're in quadrant 3. But it's a negative root 2 over 2, which makes a positive root 2 over 2.
Yep.
And then we put in pi over 4. Cosine of pi over 4 is same as cosine of 45, which is root 2 over 2.
Wait, did you already put this in there?
No, sorry, yes. Thank you, Spencer, for keeping me on track here. Yes, and put in here, drugs. So the sine of 5 pi over 4 is root 2 over 2, negative root 2 over 2. There we go, that's better, sorry.
So then it's positive.
Yeah, that'll be
Okay.
positive. Good, sorry, my bad. So I put 5 pi over 4 into here and here, minus, then putting pi over 4 into both of those. Got ahead of myself. So we're putting in cosine of pi over 4, which is root 2 over 2, but that's negative, so it's negative root 2 over 2. And then putting pi over 4 in here, root 2 over 2 again. So root 2 over 2 subtracting negative is like adding. So now we have 2 root 2 over 2, which is root 2. Minus, we have Negative root 2 minus another root 2 is negative 2 root 2, so minus negative root 2. So we have 2 root 2. Because subtracting a negative is like adding a positive, so this is correct, 2 root 2. So there's the area between sine and cosine from the places that they intersect, which is at pi over 4 and 5 pi over 4. Now, as promised, we need to find the area of a region between two curves in which they alternate, where one curve is above the other for one part of the region, and then it's below for the other part of the region.
Do we have to treat it like a negative?
We could do it that way, or we could just switch the order of the integrands, which we'll talk about in just a moment. Okay, so here's another example for us. We want to find area between f of x equals 3x cubed minus x squared minus 10x and and g of x, which is negative x squared plus 2x. So we could graph this on our graphing calculators or not, either way, but I'm just going to steal a diagram right out of Larson's book here. And I'm going to draw the diagram as best as I can. So I'm going to draw g of x first because it's a little easier. So here's 1, here's 2. So the parabola goes like this. And it continues on down this way. And the cubic goes up to 6. Goes through the origin. Back up. It's the x-axis of 2. So as you can see, we have 3 points of intersection. And in the red region, we can see that the cubic function is on top. And in the green region, we can see that the quadratic function is on top of the cubic function, which is on the bottom. So red region, cubic on top, and green region, where the cubic is on the bottom and the quadratic's on the top. So again, we can set these two things equal to each other, and with some work, calculator work perhaps, or maybe it's even factorable, I'm not sure. Looks here like it's probably factorable. We end up being able to find out that the points of intersection are, maybe we should actually do this, let's set them equal to each other.
Yeah.
So we get 3x cubed minus x squared minus 10x equals negative x squared plus 2x. So just put these pieces on the other side here, and we get 3x cubed. So we're going to add x squared over, so that's outie. And so we have minus 12x equals 0. Factor out of 3x times x squared minus 4 equals 0. And so we get 0 and plus or minus 2. So that verifies for us that our graph is good. And there we are at 0 as one of our points of intersection, and negative 2 and positive 2 are the other points of intersection. So we need to know this information because we need to be able to set our limits of integration. So in the red region, we see that the cubic function, which is on the top, so we need to write that one. I'm just going to be clever here and use red.
Yeah.
So area of the red region is going to be the integral from -2 to 0, -2 to 0, of the cubic function, which is on top. So we put that first, 3x cubed minus x squared minus 10x. That's our first function, minus the other function, which is the quadratic, -x squared plus 2x dx. So that's the area of the red region.
Can we just skip a step and make it positive x squared minus
Yes,
x? Okay.
yes, yeah.
Okay.
Computer went to sleep, but it still seems like it's okay. So that's the area of the red region. And then we're going to add to the area of the red region the area of the green region, which we'll write over here. So that's going to be the integral. And as we can see in the green region, we're going to go from 0 to 2, and the quadratic is on top, so that goes first. The cubic is on the bottom, so that goes second. So we're going to integrate from 0 to 2. Hopefully this is legible. I'm going to go with black. I don't think the green is all that good. So 0 to 2 of the quadratic function first, -x squared plus 2x, minus the cubic function, which is 3x cubed minus x squared minus 10x dx. So we're going to add the red integral to the green integral after we evaluate all that stuff, and we get the two areas that we need, the red area and the green area, and then we just add them together and we get our total answer. And I guess we could probably grind through that, though this would be easier with a graphing calculator. The graphing calculator would take care of all this business for us. So I'm just going to say that we have the ability to integrate all of this stuff together, and there's nothing tricky here. So I'm just going to say that, well, actually the integral doesn't look all that hard. The numbers are not fractions. So, all right, so we'll just do this. Okay, so, so let's integrate the first thing here, which is that. So I'll put that integral right here. So I'm integrating this piece right here on my other piece of paper in black. So integrating 3x cubed, we're going to get 3x to the 4th over 4. Oh, we should actually simplify this, shouldn't we? So we have -x squared plus x squared means the x squareds are actually going to go away. So actually, let me just do this. Equals the integral from -2 to 0 of 3x cubed, and -10x minus 2x is minus 12x, plus, so I just simplified the area of the red region, plus, and let's see if we can simplify the other one, 0 to 2 of -3x cubed and -x squared, subtract -x squared, the x squareds go away, and 2 subtract -10 is plus 12x dx. Okay, so let's integrate now then. So we have 3x to the 4th over 4 minus 12x squared over 2 on -2 to 0 plus negative 3x to the 4th over 4 plus 12x squared over 2 from 0 to 2. So plugging in 0 first, we're obviously going to get 0, minus, plug in -2. So -2 to the 4th is 16. 16 divided by 4 is 4, times 3 is 12. Minus, and we're making sure that we, since we're putting -2 into both of these, we're going to make parentheses, so we can distribute that negative sign there. And put -2 into here, So that's going to be negative 2 squared is 4 over 2 is 2 times 12 is 24. Plus, plugging in 2 this time, and we should already have some of these numbers in our head. 2 to the 4th is 16 divided by 4, so that's going to be negative 12. And we're putting in 2 here. 2 squared is 4 divided by 2 is 2 times 12 is 24. Minus 0, because after we plug the 0 in we get nothing. So we have a negative 12 plus negative 12 plus 24 is positive 12. So we have 12 plus 12 or 24, and that is the right answer. Now, a couple of things that are useful to know here, or note here, is that the 0 here and the 0 here should match up, because we're integrating from negative 2 to 0, and then again from 0 on to 2. So that limit of integration should be the same. We should be matching those up. And the other thing to note is, if this was on the calculator portion of your test, you could just simply put this into your calculator, and in fact, as I'm looking at these two things right here now, we could have made our jobs a lot easier if we had just done the following and combined our two integrals here. So the integral of this minus this plus blah 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 is, we could actually just combine that with that. So we're adding 3x cubed added to negative 3x cubed is no x cubes. Negative 12 plus 12 gets us 0. Okay, so we can't do that. All right, that doesn't work. That was a bad idea. Just ignore that idea. Oh yeah, we can't do that because they're on different intervals. So that doesn't work anyway. Sorry, my apologies. So 24 is the answer. So questions? Anyone? Spencer?
No.
All right. Okay. So we really don't have enough time to do volumes. So at least we got the area between curves. I can't remember if I made a whatever it's called, an assignment. So I'm going to do that right now. So we're going to be in the Larson book, which I'll actually put up on the screen in just a moment, because I imagine that you should be able to take a still image of this and get the problems that you need. So if you haven't already done it from before, the assignment is from Larson, the big nasty Larson book. Larson, page 409. Let's find the area of the region 1 through 6. 1 through 6, and also sketch the graph of each function and shade the region. Yeah, I like that. So let's just do, that's two quadratics. Let's do something different. Okay, yeah, so let's do just number 7. Sorry, I should just do 1 through 7. That would have been better. And then determine which value best approximates the area of the region. Da 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 da. Yep, who cares? Okay, and then let's do. Let's not do g of y here. We didn't talk about that.
Why is 29 in red?
Because the ones in red, Larson suggests these are good. These are good quiz questions.
Let's do 29.
Let's do 29. No, g of y. Yeah, we didn't learn g of y or f of y. Okay, so let's do, let's get a variety of functions here. We got 1 over x squared, that's nice, good. Okay, so let's do, how about 2 to 26 the evens? Does that seem like too much? Or 13 to 26, I'm on drugs. That's only 6 problems, 14. All right, so then we'll do 14 to 26 the evens. So there's the assignment. Larson, page 409, 1 to 6, number 7, and then 14 to 26, the evens. So I'm just going to put the book onto the camera. And there it is. And I think, I don't know if I can zoom that in, but maybe you can be able to zoom that in, maybe? I'm not really sure how that would work. Well, I can, so that's what I'll do. I'll just zoom in on one part of the book here. So we'll zoom in.
Ooh.
Okay, so we'll zoom in on 14 to 26 evens. There they are, which is actually quite viewable. We can see that. Oh, I need to move this over so you can actually see the whole thing. 14 to 26 evens. Let's go back a little bit. There they are. It just fits in there. 14 to 26 evens. So you can pause this and then write down the problems. And then I'm just going to move the camera over, and I have to zoom out here a little bit, I think. There we go. There it is. 1 to 6, right there.
You have to go a little more.
Yep, I need to go this way.
Well, they can't see anything outside.
Oh, okay, yeah. Oh, I didn't realize that I drifted down there. Okay, so we'll just go a little lower, I guess. Come on. That's pretty close, anyway. So there they are. I think you can probably read that, or you can zoom in yourself, or however it is.
Don't forget to give them 7.
I'm sure you can work the technology. Oh yeah, thank you, Spencer. So there's 1 to 6 right there, with the diagrams and the shading and all the rest of that sort of stuff. And then number 7 is just down here. There's number 7, right there. So there it is. There's all the stuff, and hopefully that lesson went well, and hopefully we didn't lose any time, or not much time anyway. We'll do volumes hopefully when we're all here, and we'll take care of the rest of the integral stuff with the details that we need to have from the previous test, and you guys need to finish test too. So we got a lot of work to do in the next few days, so let's get cracking. And hopefully you guys are all better by Thursday. Sure, know which one of these was the stop button.
It's under the...
Under here?
It's under the thing.
Under where? Oh, there it is. Yeah, it's just stupid.